Hi, and welcome to Software Development Trends for FPGAs. My name is Max Domeika, and I'm with Intel Corporation. I'm pretty excited to be here today. So I really want to share with you some information on FPGAs, and it'll be done through a lens as a software developer, because that's what I am. I'm a software developer. And what motivated me to give this talk today and put on this talk was really one of necessity. Because Intel, the company I work for, acquired an FPGA creator, supplier in Altera a few years back. And not only that, our CEO has put FPGAs front and center on what we call the virtuous cycle. So the virtuous cycle is how Intel is going to satisfy the demand for all of this data economy that we're in, how we're going to help process that data. And FPGAs are going to play a vital role. And so what I've known about FPGAs before giving this talk was that FPGAs were largely the domain of hardware engineers, but hearing that software developers will get to play in the near future. So I wanted to find out what that was about. And so that's what I'm going to share with you today is the FPGAs and what are some software development trends, empathizing as a software developer and how to view FPGAs. Okay, so really excited to be here today. Thanks for attending my talk. A bit about myself before we get started. So I've been at Intel for roughly 20 years, and the exciting thing about that is it's almost 21 years, and so in a couple of weeks I'll be taking my third sabbatical, so 8 weeks off to recharge. So getting close to that, very excited. I've been at Intel for 20 years and have spent a majority of my time doing embedded software development. In fact, authoring 2 books on the subject. One is Software Development for Embedded Multi-Core Systems, so employing multi-core processors in your embedded solutions. And then a second book, Breakaway with Intel Atom Processors, so taking a look at embedded Intel Atom and how to do software development for it. One of the highlights of my career was on an embedded project called the Intel Bind-In Compiler. And what this compiler enabled was the ability for Intel architecture processors to run with big Endian semantics. And that was something that many of our embedded customers needed and wanted some business. For the past 4 years, I've been part of an innovation team. Really exciting job, lots of diversity, lots of different verticals that I deal with. And so we work with small startup companies and try to get them to innovate using our technology. So 2 recent innovation projects. Earlier this year, I was at NRF, National Retail Foundation conference or federation in New York, and we were showing off a foot scanner that used Intel RealSense technology to essentially do a 3D scan of a foot. And before that, I was working with SWAT team members. So it was at Urban Shield, which is a 48-hour SWAT team exercise. We outfitted them with Intel Recon Jet heads-up displays and cameras, and so they were able to use a heads-up display to get themselves situational awareness before they went into a emergency situation. So again, Max Domeika, I've done embedded for quite a while. Lots of small, quick innovations, and looking forward to seeing how I can use FPGAs for my continuing projects. And then motivation for you as a software developer, why should you care about FPGAs? Well, we're seeing mention of FPGAs closer and closer to areas that we care about as software engineers. So just recently, if you attended or if you watched some of the videos from Microsoft Build, I think held less than a month ago, there was a discussion about Project Catapult. And what they did was they employed an Altera Stratix 5, which is a type of FPGA, as a front door to their servers. And what this did was it helped with the latency of processing data between the servers. So you can see the quote there. They essentially made the FPGA the front door before the processing even got to the heavy compute they had in their servers. The FPGA was processing data and shuffling around because of the performance boost that it could give. So there's a software company that's caring about FPGAs. And then Intel's own Intel Go automated driving solutions. So in advanced driver assistance systems, we're seeing FPGAs being used, and they've been actually used for quite some time. But they're great as an experimentation and a performance platform. And so, again, mention of FPGAs in an area that I think we as consumers and as software developers are caring more and more about, that's automated driving. I'm pretty sure that the FPGAs are being used as an experimentation platform. Those cars are on a test track and not just experimenting out in the community at large. So, but in any event, FPGAs being used because it can be reconfigured. So you can test different algorithms out. And it also gives you high performance, as you'll see in some of the later slides. Okay, so that's why we should care as software developers are getting closer and closer to areas that we as software developers care about. So the way this talk is organized is essentially 2 parts to it. And the first part, what I wanted to do was give you guys a primer on FPGAs. Okay, so talk about what is it and why should you care? And then also give you a philosophy as to, okay, where would I want to use this in my various solutions? So I'll give you kind of my read on FPGAs as an optimization solution for getting performance on your applications. The second part, we're going to give you a tactical approach. So let's say you say, okay, I want to use FPGAs, Max, so how do I use it? Well, one avenue to use it today is via OpenCL, which is an API for heterogeneous programming. So we're going to give you an overview of it, and you'll basically understand the process of development using OpenCL for FPGA development. Then we'll conclude, and we'll have some time for questions. Okay? So that's the lay of the land for today's talk. On to FPGAs, FPGA architecture. They're essentially fine-grained, massively parallel architecture devices. And they contain the building blocks to create extremely power-efficient solutions. They contain many things, so millions of reconfigurable logic elements. It can comprise thousands of memory blocks, so the ability to add memory to this piece of silicon. Thousands of variable precision DSPs, so you can put digital signal processing routines or functions close to those memory blocks. Dozens of high-speed transceivers, so for doing things I/O that you need onto and off of the chip. Multiple high-speed configurable memory controllers, so again, shuffling memory between the various parts of the FPGA and then also off the FPGA. And then finally, multiple cores, multiple soft microprocessor cores, ARM cores in this case, which is a newer trend, this idea of SoC FPGAs. And what is interesting about a SoC FPGA, and this is a trend that is kind of realizing itself as we speak. What's interesting that is if you are let's say you're an embedded board provider and you have multiple SKUs, right? You got to create multiple boards because you want a microcontroller, microprocessor, and specific peripherals on it for a specific type of domain or application. What you can do with a combination SoC FPGA is essentially use the same board, and the FPGA becomes the I/O and peripherals that you need for your specific application. And so this is an exciting application of FPGA technology, and I think we'll see this go forward in the future. Okay. Now I want to go back to what do FPGAs do, and the way to think about it is related against something that we know and love and hold dear to our heart, and that's how a single instruction would execute on a simple CPU. And then we'll contrast that with an FPGA so you'll understand. So here we have a simple, this is a C++ instruction, right? You've probably written thousands of these type of lines of code in your programming career. Basically, it multiplies the value stored in a memory address by a constant, in this case 42, before adding it to the value stored in another memory location and updating it, okay? And when you compile the instruction into CPU assembly instructions, you see essentially there's 3 loads to the different memory locations and a multiply and addition before the result is finally stored. And this is a very simple pipeline processor, showing 3 stages. There's an execute stage as well. So this is the traditional 4 or 5 stage pipeline that I think if you ever took a computer architecture class was the first thing you stared at. Okay, pretty straightforward. But if you look at how one of these 6 assembly instructions get mapped to that hardware, what you can see is that it only uses a fraction of the hardware at that point in time. So this one instruction is just using a small amount of the, in today's CPUs, billions of transistors that are on the chip. So if you're looking at it from that perspective, it's very inefficient use of the hardware. And so we're going to contrast that against an FPGA and what you get to do with an FPGA. So with an FPGA, you're able to lay down a custom data path for it. It matches the instructions that you need exactly. remember the high-level instruction we wanted to execute, the resulting implementation in the FPGA would look like the block diagram that's depicted below. So if you had enough, let's say, reconfigurable elements in your FPGA, which you probably do given the one instruction you're doing here, you would have exactly what's shown in that custom data path. And so the data path matches in terms of data widths, memory sizes, and configurations to get that optimal throughput for this instruction. So essentially, that's the best you can do, so to speak. Much more efficient use of the hardware. And you can also imagine that if the instruction was in a loop, the efficiency would grow even more, because ultimately you'd be having a pipeline go through this as instructions are filtering through this data route. And that's where the FPGA really shines. Okay? So that's a little simple compare and contrast against the CPU. And now I want to up-level and say, well, what's a good frame of mind when it comes to thinking about where the FPGA fits in terms of the optimization or performance acceleration spectrum? And so what I put together here is a chart that shows, that compares the FPGA against the CPU, the GPU, and a custom ASIC. And the way to think about an FPGA, or the way I've come to think about it, is as a general purpose accelerator. Compared to something like an ASIC, we'll take at the far right here, an ASIC is customized for that particular application. So in terms of being flexible to meet the needs of a wide variety of applications, the FPGA does a better job than an ASIC. Whereas a CPU is sort of the most general purpose processor that you can think of, and so that's why it's green in this regard. If you do watch the Microsoft Build talk, what's interesting is that the speaker has a slide similar to this, where they put the GPU and the FPGA in different positions, and they make the same contention that one is more general purpose versus specific. I contend the FPGA is more general purpose than a GPU. GPUs are highly optimized for graphics processing and then are being used for high vector floating point instructions type of processing. And so it's more specific to those areas, whereas an FPGA can do things like floating point code quickly. It can also do integer code quickly. Okay, so a little more general purpose than a GPU. Floating point operations, you can see the scale. Oh, excuse me. And then when it comes to power and latency, this is also important to know. FPGAs used as the front end before the data gets into a server in that Microsoft Project Catapult example. And it's doing that because the latency is faster than going to a CPU, having to deal with a operating system. And in the case of a GPU, you're having to go through the CPU to get to the GPU and back again. And so latency is the worst in terms of end-to-end latency, the ability to react to something. And ASIC, of course, custom built for the application, so its latency can be real quick. Also, power requirements, so FPGA and ASIC, generally low power because it's customized for the purpose, whereas CPU and GPU, more general purpose, and then GPU really targeted toward high performance, so using the most power out of them all in general. So net, the way I propose to think about FPGAs is a general purpose accelerator, okay? Giving more details about what it's good for, let's look at these two case studies. And this is from Altera as well, trying to showcase, trying to highlight what exactly do FPGAs shine at. And what we see here are two integer type algorithms. One is AES encryption, the other one is document filtering. So AES encryption, lots of integer arithmetic, coarse grain bit operations that can be all laid down as a custom pathway in the FPGA, complex decision making that can also be laid down. And so it's a medium, sort of a medium size. If you ever used anything or written your own or borrowed code that did encryption, so if you were doing PGP or something like that, typically they're medium size compared to your larger application, and so that's perfect to fit in the body of an FPGA, as opposed to, let's say, your big database source code that you're going to run. You're not going to run your entire application in FPGA, but if you can speed up these medium-sized algorithms, that's an area where FPGAs do very well. And you can see the performance numbers that result both in terms of power and performance, outclassing CPU and GPU, and then power in terms of efficiency, just order of magnitude better than those. Document filtering, the same thing, integer algorithm. A document filtering, Bloom filter, essentially it's an intelligent hash function. And again, that's something that can be laid down in an FPGA and run efficiently and high performance. Okay? And so what is the problem or opportunity? Okay, so where do FPGAs fit into my software toolkit, and why should I care what's coming up next in my career as a software developer? And to think about that, you want to think about what's the end state for FPGAs. And this is my belief, and I think if you talk with enough folks that are experts in this, I'm by no means an expert. If you talk with enough experts, they'll sort of say the same thing. They'll say that I believe that FPGAs will become as integrated into the acceleration spectrum as any other option that you're used to today. So think back, for some of the old timers here, think back to the 386 processor. At that point, the 386 and the 387 were separate processors, and the 387 provided a floating point. But over time, what happened is it became integrated. So the 486 integrated it. And then if you look at what the architecture folks are doing, they've been putting the floating point unit more and more interwoven into the core pipeline, into the microprocessor pipeline. Same thing with vector instructions such as streaming SIMD extension, Intel streaming SIMD extensions, AVX technology, multi-core, the use of multiple processors. It's easier to use that today, either via process parallelism or things like OpenMP. GPUs have been getting easier to program in general via things like OpenCL, for example. And then ASICs usually program via function calls. But FPGAs will be part of this spectrum for you to choose, your software teams to choose, just like these other guys, just as we're used to them today. Okay, and then two other concepts I hear people talk about. One is this concept of universal flow, and that's sort of the paradise for when FPGAs fit in. It's this idea of you program once, and either the runtime, the operating system, the compiler will take care of how to accelerate it for you, and FPGA will be one of several options. And then another concept I hear frequently is the silicon convergence, and we see that with the SoC FPGA, this idea of a compute that has both a CPU as well as reconfigurable elements. And I think it's only a matter of time till the chip architects, the operating system vendors figure out a way to combine a processor that has both, able to do things like task switch so that you essentially get your custom acceleration loaded up into the FPGA at every task switch. Wouldn't that be neat? Excuse me. The problems for seeing this visions, for seeing this end state, right now, as a software developer, knowing when to employ FPGAs versus other acceleration options is difficult. And even what I provided you here in the last few slides is rather high level, general purpose accelerator. Well, what does that mean? I think we as a community need to know, okay, well, when does it make sense to employ the acceleration that's available on the CPU, be it vector instructions, multi-core, or some other means like that? When does it make sense to use an FPGA? When does it make sense to use a GPU? When does it make sense to go to an ASIC? And it's a multivariable computation. So there isn't one easy answer, but I think familiarity and experience will give this to our body of software developers. So once that problem is solved, there are other challenges. So FPGAs, let's say you want to use an FPGA. Right now, FPGA development as a software developer is difficult. So I'm going to show one means of doing that. That's OpenCL. But one of the challenges is that the compilation time is longer than what you're used to. Right? We're not back in the days of punch cards and waiting overnight to see the results. We more or less expect instantaneous compiles and testing our code within seconds or minutes. And FPGA compile times aren't there yet, and so that's something that's going to be need to be solved, as well as debugging. So you're debugging something that's a different processing unit, and that's always more difficult than debugging something that's on the CPU. So the technology will need to mature there as well. And that's a challenge, right? Because if you have multiple acceleration options, right? And it takes you 10, let's say, exaggerate to make a point, 10 times as much development effort on FPGAs to get the performance, you're going to use that as maybe the last resort. And so to make it more attractive to software developers, the development environment for these FPGAs need to be just as easy as what we have for GPUs, for the multi-core processors that we use in our toolbox today. And then the third point is there are competing visions for how developers will interact with FPGAs. And multiple choices is a good thing, right? You don't want to be forced to do your programming in one particular way. Choice is good. I think the challenge right now is that there are a lot of offerings out there, and I think we as an industry haven't settled on which are the ones to put our ergs behind and rally a community around to say, okay, this is the one that's making the most sense and it suits these particular class of users. Let's go and as a set of corporations engaged in this, let's go and rally around it and lift the developer ecosystem for it. So that'll happen in time, but I think it's still being sorted out. Okay, and so net, someday programming FPGAs will be as easy as programming CPUs. We're not there yet, but we're going to get there. And so, my passion is software developers and helping software developers write code and having the ecosystem to do that. So I'm very eager to help Intel and help the community solve this problem. All right, so that is the primer on FPGA. I hope that gave you a bit of exactly what is an FPGA, why should you care, and then high level, some of the challenges that we need to solve so that FPGAs become just as much a part of our toolbox as other acceleration techniques. Now I'm going to shift ground and talk about OpenCL, which is one approach to using FPGAs. So let's say, hey, Max, I'm interested in FPGAs. I want to try something tomorrow. What should I do? Well, there is a pathway to programming as a software developer FPGAs, and that's OpenCL. There are others, but I want to specifically talk about it because that's the pathway that Altera is offering. So we'll give a bit on how or what is OpenCL, and then what's it look like in the FPGA development pipeline. And then we'll conclude. So what is OpenCL? Effectively, it's a software programming model for software engineers and a software methodology for system architects. It's the first standard for heterogeneous computing, allowing for code portability between CPUs, GPU, and FPGA accelerators. It's a low-level programming language. It was created by Apple and derived from C. It's not full blown out C or C99. It's a subset. So for example, it doesn't have C99 headers. You don't need it for writing the kernel codes. Function pointers, recursion, things that require like a heavy duty runtime to instantiate. Variable length arrays, that's part of C99, or bit fields. It adds address space qualifiers, APIs for parallelism, such as work items, work groups, vector types, and synchronization. So you'll see these things in some of the examples I show. It's open, royalty-free standard. It's managed by the Kronos group, so you can go to their website and see the other APIs that are managed by them. Intel is an active member of this body, and we have a conformant implementation. Now let's take a look at the platform model. So OpenCL defines let's say, a virtual hardware model that implementers need to map to so that their hardware will be conformant to the OpenCL spec. Right? So it's a way that programs, if they're going to be OpenCL programs, they can run on these different pieces of hardware because there's agreement on what the actual host and the board or compute device, compute unit looks like from a high level. Okay, and so let's take a look at a typical heterogeneous platform. And in this example, we have an Intel architecture-based system, so a computer, and then a PCI Express connection between the host and the accelerator. In this case, there's two. There's a graphics processor, and then there's an FPGA board. Okay, the platform model defines the roles of the host and the devices, which can be FPGAs, DSPs, GPUs, or CPUs. There is a single host in this model. That's typically the desktop computer, and it coordinates execution on one or more devices. The platforms are vendor-specific implementations. So again, they need to connect the dots between their specific hardware and this OpenCL platform model. Okay, they map the platform, and the platforms can only target devices which a defender or a vendor knows how to interact with. The platform is also scalable with the array of devices, and each of these having its own array of compute units, which are functionally independent from others. So the idea of parallel processing and these independent processing elements that are essentially a divide and conquer approach to partitioning out work. OpenCL supports two types of parallelism. One is data parallelism, so parallelization over data, or task parallelism, so that's parallelism over different tasks. I'm going to tell a funny joke just because it's Friday, and I kind of twisted my tongue on parallelism. I gave a talk, so I was involved in multi-core and talking to folks how to do development, and so it was just, I don't know if it was a bad speaking day or something, and I started, instead of saying parallelism, I said paralyze. We got to paralyze the application. So instead of parallelize the application for better performance, I was like, oh, you got to paralyze the application. I was like, and so someone asked, they stopped me like midway through, and it's like, well, what do you mean by paralyze? If you paralyze something, it doesn't mean you kill it, you stop it. And it took me a second to say, oh, I've been saying this the wrong way. So here's a note. If you give a talk on multi-core and parallelism, make sure you enunciate every syllable of parallelism, parallelize, okay? So there, you learn more than just about OpenCL and FPGAs. You also learn how to give good talks without saying the opposite of what you mean. Okay, back to today's program. So OpenCL supports both data parallelism and task parallelism. Data parallelism is achieved when we explicitly launch data parallel tasks across a workspace. The tasks essentially are parallel threads, which are instances of computational kernels. So they have their chunks of data that they're going to work on. They're all executing the same code, different data. Task parallelism is achieved in a host-controlled manner through the use of queues and events. Queues specify the list of tasks, and events are used for synchronization purposes. So the way to think about task parallelism is that the different kernels that are running, they are different from each other. So that's the idea there. The tasks are different versus data parallelism, where the tasks are the same, it's the data that's different. Data storage and movement on the device is also explicitly specified. The OpenCL abstract memory model can model various types of memories available on the device. Movements to and from the memory objects are also explicitly specified through the command queue. Because of this, it's up to the programmer to manage the memories and the bandwidth efficiently. Okay, so it's up to you. And that's an opportunity to optimize, make your code run faster. The key concept when launching a kernel is the work item. When we launch the kernel in a data parallel fashion, like I said, the unit of concurrent execution is the work item, and they're all the same between the different threads that are executing these. So when writing the kernel, we usually map a single iteration of a loop in standard C to a work item. You'll see an example of this. And usually we generate as many work items as elements in the input and output array. The kernel operations are mapped to hardware during runtime. Here's an example, and in this case, it's a simple vector add, so kind of the simplest poster child for employing OpenMP. Notice, so some syntax items. Kernel function is preceded by the keyword kernel. So it's a special note that this is a kernel that we're going to execute on the heterogeneous processor. Kernels must return type void, so there is no return value. Here we have 3 arguments, so more than just integers are supported. There are other data types, but in this case, the 3 arguments are integer arrays. A and B are the inputs into this, and C is the output. And you also notice the global keyword there that signifies where essentially the address space for these guys. The body of the kernel represents a single iteration of a loop, and this would perform the vector add, and so that's what that second line of code does. You see the first line of code that sort of gets its place in line, so the global ID, and this is how the, since the arrays A, B, and C are all global in nature, this is how the data that's specific to this kernel gets located. Okay. And as a result, the execution of kernel only performs one add within the vector add, so you see that through what's communicated code-wise here. Now it comes what's actually implemented on the FPGA. So the kernel code that you write is going to be unique. But FPGA, or for OpenCL, what we said, it defines a platform model. So it would not make sense to say, okay, the kernel is unique. Let's compile that into an FPGA architecture. And then also let's just merge that with the OpenCL implementation and compile that as well. What we've done as a solution is to have some pre-compiled elements for the static part, or the parts of the OpenCL platform implementation that is the same between OpenCL runs, right? The platform model that OpenCL defines. And so the kernel itself is converted into custom hardware, but also parts of the FPGA is used for the OpenCL platform. And there's pre-compiled hardware interfaces for things like the PCI Express interface, memory controllers, the kernel interface, so loading and unloading your kernel that's going to run on the FPGA, the clock generator, so keeping tabs of the instructions as they flow through, direct memory access, and then also hard processor system. In addition, the memory models are also implemented, so the difference between global, local, and private are implemented on the FPGA. Okay, so this gives you an idea of how essentially OpenCL platform and your kernel are mapped onto an FPGA. Here's some mechanics of using the tool. So this is Altera's offline compiler, or AOC. So the tooling provides you the ability to see information about the board support package. So you know what's going to run on the hardware. You can query that. And on the right, talks through the compilation process. So once you know what board you're running on, you specify that to AOC as well as your kernel code, so kernel.cl. And what happens as a result of this is essentially the hardware system is compiled using the Quartus Prime software, so that's an Altera software solution, and it generates the executable, so the AOCO and the AOCX. These are the files that essentially get burned or partitioned onto the FPGA and then run. There's also a log file that includes the estimated resource usage, and I'll speak to that in a second as well, so you get an idea of how much of the FPGA you're using. So this is how you do a compilation. One of the challenges in this is that it does take, in terms of, it takes hours instead of seconds or minutes, which you might be used to typical software development. And so one of the tools that you're encouraged to use during the development of your code is the emulator. And an emulator is just that. It essentially acts like the underlying FPGA, but what happens is it's running on the Intel architecture platform or the host machine. And so this is the way you specify, hey, I want to use the emulator, so let's compile the kernel file for it. I can then do testing and debug to make sure it's functionally correct before you do the heavyweight compile for the FPGA. The debugger supports things like the OpenCL syntax, also channels, which is it's a extension specific to FPGAs for fast data communication, and then also everyone's favorite printf debugging. So that's how you'd debug your code quickly, and then you'd eventually get it burned onto the FPGA. Another area of tuning that you typically have in your toolbox is a profiler. Where's the time spent in my program? And so there are options to add profiling logic into the hardware design. The command line is here, and then as a result of running the code, you'd get a output file that has, if you've ever used things like gprof, so kind of standard GNU-based profiling tools, you'll see that sort of output where the majority of your time is spent. Okay. And then I mentioned an area report. So one of the things, you do the compilation, and you want to get a feel for how much of the FPGA you have used. Right, and so you don't want to use too much, and you don't want to use too little. And so this is an example of a usage report, and you can see what elements of the FPGA are using and the percentage, right? And once you get to 100, then you're not going to use any more, right? You're going to run into problems with that. And this is important because when it comes to compiling your code using OpenCL, there are some things you can do for better performance. So there is a performance tuning aspect to it to make your code run faster and faster. It isn't just coded for using OpenCL, run it, and that's as fast as it can get. Just like in standard CPU code, there is a tuning cycle that you can take advantage of. And so to think about, and this goes hand in hand, because typically, if you remember from computer science days, adding optimization makes the code bigger. That's the general rule. from a computer architecture or compiler class. And so as you optimize, you use different things to optimize, you're going to see that the usage of the FPGA increases. And it's basically a balance you need to strike and make sure everyone's okay with. So an example of that, here's a code that we tried, essentially a matrix multiply. And we said, well, what can we do to improve the performance? We measured the original simple OpenCL code. And we said, well, what are some of the tools used to make it run even faster? And so if you do look at the OpenCL guide that Altera has, so it's a PDF file, it gives you tips on how to use these different attributes and pragmas and explains what they are to make your code hopefully run faster. And so things like loop unrolling, if you're familiar with that, so it removes the overhead of loop iterations. SIMD work items, so you can have your FPGA process elements like a SIMD processor, so in parallel instead of sequentially. You can also ask this FPGA to use multiple compute units, and that's done with the num compute units attributes. That effectively, if, let's say you have a function that you have placed on the FPGA, essentially makes a copy of that entire function as it's represented in the FPGA, and then essentially it takes advantage of both of those compute units to process the data. Okay, and so this shows you an example, right? So this is where, if you're a performance person, you have a job, even in this age of FPGAs. So you can see the original code here, the original matrix multiply, and then you can see the speed up that results from these different optimization techniques. So went from about 25 milliseconds to under or around 5 milliseconds by using SIMD, unroll, compute units, and combining those together to get the maximum performance that you can. Okay, so that just walks you through, we just walked you through OpenCL, what is it, what's it look like on an FPGA, and what does the development process on an FPGA look like. So use of the emulator, the profiling tools, and then some of the optimization techniques you use to make your code run faster, just as you do in traditional software development, okay? And so with that, I'm going to close and just summarize what we talked about today. It's been great. Had a good time learning about FPGAs and then having the opportunity to share that with you. So FPGAs, they offer a compelling path to performance. I think we'll see that and know that more as we move forward here. One way to frame an FPGA is a general purpose accelerator. It's good at many types of acceleration. It may not be the best at any specific kind, but it's good at many different kinds, and it's reconfigurable, so it can be repurposed to other things as needed. FPGAs are becoming more accessible to software developers, so you as a software developer will most likely have the opportunity to use FPGAs, if not in the near future, maybe in a few years. You might even someday may even be using it and not realize it because the use is controlled by the runtime or the operating system. Okay, we're in this day and age. If you want to get started today using FPGAs, there are some dev boards. So the dev board I have is I'm not going to name that. It's it has a Cyclone 5 on it, and it has OpenCL BSP available for it, and it runs on the order, I think it's less than $300. And so OpenCL is one pathway for software developers to get started learning about doing FPGA development today. And like I've said many times that someday FPGAs are going to be automatic tool for software developers, so why not get started now? Okay. With that, I'll close and open it up to questions. So here's one. This is one I don't know the answer to. So we have someone that would like to try OpenCL SDK. Is there a free license in order to try using Intel OpenCL SDK? I don't know the answer to that because I'm not on the team. I suspect the answer is yes, but I am not sure. So what I am going to do is figure out a way to get, I'm going to write your call sign down and figure out a way to get in contact with you in particular, and we'll get you an answer to that, okay? Yeah. So sorry, I'm not a marketing person, so I don't know the answer to all the software products that we put out. Okay. Okay, so thank you, Amar. Amar posted a link to the OpenCL and a website where you can check it out. And yeah, so if you're so motivated, you can check out that link and probably get an answer faster than I can. Thanks, Amar. Okay. Well, I'm gonna talk a little bit more then, since we have some time here. So one of the things when I said FPGAs are a general purpose accelerator, that is, it's true, uh, but acceleration also kind of implies a coprocessor. So this aspect that the FPGA is accelerating a CPU that it's attached to. And that is not the case. So FPGAs are already used in many cases where there is no CPU and it is doing essentially all the processing that it needs to do. So an example of this is there are uses in automotive already for this. And so FPGAs also can be, let's say, replacements for microcontrollers or ASICs. There's a sweet spot between something that's generally programmable and small versus something that is a custom-built ASIC, and FPGAs also fit that need. And you'll find if you look at Altera's product family, they have high-end FPGAs as well as lower end that have fewer gates. Okay. Okay, so we do have another. Oh, okay. So he's trying to port C code into the D0 nanoboard, encountered the following error. Okay, well, that's your question. Okay. I think it's generally the same thing, having a license for the FPGA SDK. Now, the person that is online, there is a, I think Amar, you pointed out, let me see the link you pointed out. There is also a write-up to using that board in particular, so a getting started guide, and it'll step you through that. I don't know if it'll have your answer with respect to a valid license. Again, we'll get your link and I'll get you a conclusive answer to that offline, okay? I'm gonna move to close here, and I'll just follow up with what I'm doing since, hey, it's Friday, I talk a little bit more. So I'm going on sabbatical here, but when I get back, my intention is to help Intel figure out, or my part of the org, which is primarily software developers, figure out FPGAs and help bring that to software developers, because I do believe that we as software developers will get an opportunity to use FPGAs for acceleration. There's a lot to do in terms of the developer experience, and then so fitting FPGA development into the, the standard development process that we all use today and know and expect, and the tooling support. So it's really exciting to bring this unique piece of acceleration in, and then watch how the chip architects go and integrate it into the core CPU, and how we evolve this together. So it's going to be a tool that we use and we take for granted someday, just as nowadays we take for granted the 387 floating point. We don't really use the floating point unit. Instead, we use Intel SSE or AVX in place of x87 floating point. But we're going to take FPGAs for granted in the future, and excited to help Intel figure that out. Okay, Amar provided a link for the DE10 nanoboard with some samples, so you can take a look at that. Thank you for your time today. Just pleased to be a part of this conference and enjoy the other wonderful sessions that we've lined up for you today. Thank you.